Hello, everyone. Good evening. So for those of you who don't know me, my name is Ana Moraes, and I'm the Deputy Director of the wonderful Institute for Sustainable Engineering, WISE in short. So today or tonight, I'd like to welcome everybody, including all of you who are here in person or online. And thank you so much for being a part of this unique event. So some words for the students who are presenting today. So we know faculty and staff that sometimes managing academic responsibilities and work with research can be challenging. Most of the times it's very challenging, but I think today is a very special time and a very special event to think about what you have done in the past few months in terms of research and academic work. So I think it's a nice time to reflect on your accomplishments and how far you have come. So without further ado, I'd like to start or get started our symposium today. I hope you all have fun during your presentations. In my perspective, when I present my research is the best part because I feel proud of what I do. So I really hope that you feel the same. And yeah, so have fun. And I'm looking forward to watch your presentations. Thank you. Sorry, should I introduce the first speaker? So the first speaker is, or the first two speakers are Madison and Samantha, and they are going to talk about refrigerant separation using column chromatography. Thank you.
Okay, can we hear? Sweet. Okay, so Samantha and I are presenting on ionic liquid coated capillary columns for refrigerant separation. Here's our overview. So our objective is to discover which ionic liquids work best to separate refrigerant mixtures by studying the solubility or the level of interaction that a refrigerant has with particular ionic liquids. Using chromatography, the capability of the ionic liquid is tested and its effectiveness is evaluated based on the different peaks in a gas chromatogram that we create. It is a time versus absorbance chromatogram. So when an ionic liquid is determined to be useful, it can eventually be used in extractive distillation methods to separate these refrigerants. So a little background or like a brief history on the 4 generations of refrigerants. We started off pre-1930s with refrigerant mixtures that were they didn't have ozone depletion potential or global warming potential, but they were very toxic to humans and to animals and stuff. So those were phased out and replaced by chlorofluorocarbons and hydrochlorofluorocarbons. Very much a mouthful. Which ended up having high ozone depletion potential and high global warming potential. So those were phased out in 1987. And then the most recent was hydrofluorocarbons and hydrofluorocarbon mixtures, which had low ozone depletion potential, but high global warming potential. And so we ended up phasing those out for hydrofluoroolefin mixtures. And in order to recycle those mixtures and kind of make them useful still, we are separating them with ionic liquids in order to still make them useful. And so a little bit more background, the mixtures are separated and then paired with refrigerant mixtures that are not toxic to the environment. So they have low global warming potential and low ozone depletion potential. And those are what refrigerants we use today in order to stay less toxic to the environment.
So we are investigating a new method in which we coat the inside of a capillary column with an ionic liquid, since many refrigerants are selectively soluble in ionic liquids and could therefore separate these azeotropic mixtures. So this is our setup for our gas chromatography experiments. So a carrier gas, usually helium, is pumped into the GC system, and then the sample, which is the refrigerant, is loaded into the ionic liquid coated column. So as the refrigerant goes through, these peaks will be created in the gas chromatogram where we see that these separations are happening. So once the experiment is done, we can look at that chromatogram and kind of determine whether the refrigerant was successfully separated or not. So we can't just use the ionic liquid in its pure form. We have to dissolve it in a solvent because the ionic liquid is so viscous that it can't be administered throughout the column quickly or evenly. So dissolving it in a solvent will allow for formation of a nice uniform film. So we coat the column using a syringe pump in which the syringe is attached to PTFE tubing, which is then attached to the capillary column. So this is our setup for column coating with an ionic liquid. So a vacuum pump is attached to regulate the pressure, and then it also removes the opportunity of air bubbles forming. It also allows for the solvent to evaporate evenly, which is very important to get good data. The pressure gauge is attached to ensure that the pressure remains constant because that is super important. PTFE tubing is attached to one end of the capillary column, which is then attached to the vacuum pump, so everything's all connected. So how it works is we load the ionic liquid into the capillary column, and then we put it into a constant temperature warm water bath, and we wait for that ionic liquid interface to go all the way through the capillary column, and that kind of shows that the ionic liquid was coated all the way through.
Okay, so for the results that we're wanting to see, the peak on, I think it's your guys' left. Yes, the peak on the left is going to be an example of an unideal chromatogram. So this shows the separation of the refrigerants at like a smaller time period, and the peaks aren't as distinct. So if we get a chromatogram like the one on the left, we are able to observe that the ionic liquid did not work as well as we want it to. And so on the right, we have an ideal chromatogram, and this shows the peaks for absorbance that are very distinct and very large and are separated at different time periods, which lets us know that the more polar refrigerants are interacting longer with the polar ionic liquid, and then the more non-polar refrigerants are coming out at a shorter time period because they're having less interactions with the ionic liquid in our column.
So our overarching goal is to be able to identify ionic liquids that can efficiently separate these refrigerant mixtures using both gas and column chromatography methods. Currently, we are working on perfecting our ionic coating technique because air bubbles form very frequently, which inhibits our results. We're also trying out different PTFE tubing sizes to figure out which creates the most ideal vacuum seal, because that is also going to help us eliminate the possibility of air bubbles.
So for our future work, we are working on synthesizing, well, we're not working on, but we're getting new ionic liquids synthesized, and they're being sent our way. They should be here soon, and so when we get those new ionic liquids, we'll be testing them on the IGA and through column chromatography to see how well they work at splitting these refrigerants and which refrigerant mixtures they split best in order to then move on to the extractive distillation process. And hopefully, whenever we get these new ionic liquids, they work well for us. So we want to say thank you to Dr. Shiflett and to Claire for helping us make this presentation and helping us through the process of our research. Any questions? Oh, yes, Dr. B.
You can go to Dr. Alginate first.
You inject ionic liquid into the column, right?
Yes.
How do you know how much to inject? Or do you have an idea when it's too much or not enough?
Yeah, so when we inject it, we can see it come out the other end. So once we start seeing drops come out, that's when we kind of know that there's enough to go all the way through.
Do you measure that amount? Is there any way that you can say, oh, I see the first drop, it must have been...
It's about 0.7 milliliters, I want to say. It's not a ton.
The syringe pump has actual, it'll show the amount that it's injected so far. And so it'll be like 0.4 to 0.7 whenever we see our first drop come out the other end.
I'm going to piggyback off that question. And so once you've put some ionic liquid in the column, do you have to reapply the ionic liquid next time you do the separation? Or once you set the column up, it's good to go?
It's good to go for about, I think it was 5 trials with Dr. Anderson. Is that what they said?
How do you guys know that the solvent is dissolved or evaporated?
We have been looking under a microscope to see if it's absorbed to the walls of the column. If we see a lot of air bubbles in it, we know that it hasn't absorbed to the walls very well and we will need to restart. And hold on, what else was I going to say? I think that's kind of it. Like with the air bubbles, if we see them, we're able to tell that it wasn't coated all the way.
Yeah, there's different patterns that show up under the microscope that kind of tell like how the solvent is interacting with the ionic liquid, because every ionic liquid interacts with it differently. So we kind of have to figure out the correct ratio per ionic liquid. Yes, Dr. V.
So when you're doing the separation, are you working with just one mixture right now and trying different ionic liquids, or are you trying multiple mixtures?
We've been using, was it R410 or 32?
Okay. Okay.
Any other questions? Oh, yes. Thank you. I believe it would just be background noise.
This is just an example from background. Oh, okay.
Yeah, this is.
Yeah.
Yes, Dr. B.
So on the chromatogram, so with all those peaks, that's for a single component. You would expect to see that, or would that be each peak is a different component?
Each peak is a different refrigerant.
Okay, cool.
All right, I think that's it.
Thank you.
All right, so I'd like to introduce you the next 2 speakers, Sarah and Leah, and they are going to going to talk about membranes for energy efficient hydrocarbon separation from refrigerants. So the floor is yours.
Hello? Oh, okay, there we go. Hello? Oh, you have to, it's on the top. Oh, press the on button. Hello, okay. Okay, you guys can hear us? Okay, perfect. Hi everyone, my name is Sarah and I'm here with Leah, and today we're super excited to share more about what we've researched this semester, specifically about membranes for energy efficient refrigerant separation from hydrocarbons. So first, to kind of explain some of the motivation behind the research we've been conducting, refrigerants are used in a wide variety of processes and industries, including air conditioning, like our houses, this building, different food and beverage processing processes, and pharmaceuticals, for example, like refrigerated transport for certain vaccines and medications, and then also chemical processes as well. And so currently, most recycling methods are incapable of separating azeotropic mixtures. It's good that our refrigerants are azeotropes. That means they're more stable. However, azeotropes really can't be separated very easily. And so this makes it a challenge to recycle and dispose of and reuse refrigerants in an efficient way. Currently, this kind of generation of refrigerants that we're using are made of hydrofluoroolefins, HFOs, hydrofluorocarbons, HFCs, and then some of them have small amounts of hydrocarbons in them as well. And so kind of the overarching goal for our research efforts is to separate components of refrigerant mixtures to recycle and repurpose the HFOs and HFCs through synthesis and the use of membranes. So the goal is to feed a gas over a membrane, and then the permeate, in our case, will contain the hydrocarbons, and then the refrigerant gases will remain in the retentate. So here's an example of one of the refrigerants that we are looking to separate. R422B contained HFC 134A, HFC 125, and isobutane, which is our hydrocarbon in this case, which is just in small amounts. But HFC 134A and HFC 125 both have relatively high global warming potentials, so it's advantageous to be able to separate those and dispose of them properly, maybe reuse them in a different process. And then isobutane itself is pretty flammable. And so being able to separate that from the refrigerant mixtures can allow us to recycle the isobutane and again, treat that properly. And so the graphic that you see on the right is kind of an example of, again, how we want to specifically remove the hydrocarbons from the refrigerant mixture. And then other research efforts can focus on separating the refrigerants themselves. So again, just to kind of focus, give you the overarching goal of our research, we want to synthesize polyimides via chemical imidization, or we can purchase commercial polyimides as well. Polyimides are used for their chemical resistance, their thermal stability, and their tunable free volume. So that's kind of the focus of our research here. And then an approach to synthesize these polyimides is to use a Schlenk line to synthesize in a dry environment, which I will explain in a second. And then we can cast our polymer solution to make the membranes themselves. Once the membranes are synthesized, we can determine the permeability and selectivity by measuring them in a static membrane apparatus. And then eventually we can evaluate the performance with real refrigerant mixtures and potentially scale up to hollow fiber membranes as well. Right now we're just working with flat membranes. So here's an overview of the chemicals used in our research currently. So to synthesize the polymers themselves, we have two monomers. We have 6-FDA and TRMPD. And then I will kind of go over that membrane or that polymer synthesis in a second. But the monomer or the polymer that we're using is 6-FDA TRMPD together. So once that is synthesized, then we can form our membranes by adding a solvent to this polymer. Previously, we've used NMP, but more recently we focused on THF because it has produced kind of better and more consistent membranes when we've produced multiple trials. So here is kind of a more in-depth schematic of what the polymer synthesis looks like. So the first step is to form the polymer by mixing it in a nitrogen environment using a Schlenk line, which you can kind of think of it as a kind of easier to use glove box, if you will. Once we kind of dry it out and have everything in that round bottom flask that you can see, it ensures that the polymer is being synthesized in a very dry nitrogen environment. So once the polymer is formed, then we can precipitate it in water and then recover the polymer with vacuum filtration. Once that's done, we can vacuum dry the polymer in an oven at 120 Celsius for 24 hours. So it takes quite a bit to fully dry. But after that, the picture you can kind of see at the bottom, that is what our final dried synthesized polymer looks like. And so that we can then use to create our membranes, which Leah is going to talk about next.
So once our polymer is synthesized, then it is ready to be mixed into our membrane solution. So we work with different weight percents. We've been testing different amounts of polymer to solvent solutions, but we start stirring that. We leave that stirring for about a day to make sure that it is completely mixed with the solvent and the polymer. Then we cast that membrane into a petri dish to let it partially dry. Some of ours, especially the ones with THF, evaporate a little bit too quickly, so we put some filter paper on top to reduce that evaporation rate to make sure we can get a more uniform membrane and make sure that we have enough usable area. After it is partially dried, we're going to put it into a vacuum oven to finish drying out our membrane until they'll look like these two images on the bottom. Those are two of our most recently made membranes. The red circle shows our usable area for gas testing, which is what then we cut out little chunks of that and we put it on a single disc that we're going to put into our membrane apparatus with different gases, and we are going to do permeability tests by passing different gases through it. So when we test these membranes, we use a constant volume system, and we are testing specifically with HFC-32, HFC-125, additionally with isobutane and propane. That's a newer thing, so we don't have as many results with those two gases, but with 32 and 125, we also test at 2 bar. We make sure we are at 25 degrees Celsius, and we make sure our area is uniform at 1.27 centimeters squared, so we have the same amount of testable membrane on each of our trials. And we also want to make sure it is at a similar level of thickness, so between 100 and 150 micrometers, to make sure that the membrane is nice for our gases to pass through. And here's some of our results that we have had so far. Like we said, our NMP trials versus our THF trials have given us different results. As you can see on the figure on your right, that is our THF. Our selectivity of HFC-32 to HFC-125 is around 30, which compared to the NMP trials on your left, our selectivity of 32 to 125 is around 5. These results are more consistent across the board for our THF trials, which is why we're leaning more in that direction. We are also working on membranes made with PPO and chloroform, but we have not had any usable membranes from that sort of synthesis, or that sort of membrane yet, because like you can see in the top corner, that is a PPO membrane made in a hot press, which we do not have a usable area with, or as with our chloroform, they are too dry and cracked to have a usable area to test. So we are working on ways to make those membranes more usable, but we are focusing mostly on our THF trials here, and we have more specific results for our THF membranes here. Like we said, our selectivity of our 32 gas to our 125 gas is around 30, with our HFC-32 permeability being 68.8 barrier and 125 being 2.7 barrier. This can kind of be described due to the bulkiness of the HFC-125 compared to the smaller molecule that HFC-32 is, so that permeability difference can be really visually shown in how different the molecules are. The smaller molecule is going to pass through much easier. You can also see with the propane and isobutane having those lower permeabilities as well. These results are from our membrane that is the 8-weight percent that we made back in October. One of our things that we also need to take into consideration that we're working towards is that our membrane, when we were testing with propane and isobutane, was about a month old. So we are looking into if the aging of the membrane has any effect on the permeability. So later tests are going to be with those gases sooner to see if the permeability is going to be different with the different age of the membrane. So like we covered, we have synthesized our 6-FDA TRMPD polyimide membranes to test with different gases, and we've determined the optimal system for film casting. Like I said, when our membranes were evaporating too quickly, we started putting filter paper on top to take down the evaporation rate, which has led in bigger usable areas in our membranes and better testing. For those, we have completed gas tests with both our 32 and 125, and specifically with our THF membranes, we have completed gas tests with propane and isobutane, and we've seen very promising permeability with those tests.
And then moving forward, once we kind of know a little bit more about our single gas testing and what the permeability is, and once we kind of have very consistent results in creating different membranes, we can move to some multi-gas testing. So feeding those mixtures through to see how the membrane separates those mixtures potentially and what the permeability is there. We can also look into solubility and diffusivity studies to kind of better understand how our membranes are functioning and truly separating these gases. And then like I mentioned earlier, we can also look to hollow fiber work and testing to move from our flat membrane discs to hollow fiber membranes. So we'd also like to thank Univa, who is our graduate student who we research with, and of course, Dr. Triplett. They've been so helpful in our research journey and getting to kind of have this experience as undergraduates. So we'd like to say a huge thank you. Oh, no, done slide, but thank you so much. Thank you. Happy to take any questions at this time, if there are any. Yeah.
Sorry, slide 25.
Yes.
Thank you for the presentation. So if I understood correctly, you said we tried first with HFC 32 and HFC 125.
Mm-hmm.
Then we let the membrane age for a little bit, and then we try it again with propane and isobutane. Is that?
Yes, these tests take multiple days. So by the time we got to our propane and isobutane tests, the membrane had aged quite a bit. It's not that we like sit and let it wait for a while. It's that by the time we had completed the 32 tests and the test with 125, the membrane was at as significantly, like it was aged quite a bit. So it's, yes.
But what will be your result? What kind of results you will expect without like just fresh membrane to try?
So the results that actually we have gotten in this past week is that the permeability of those gases is a little bit higher in comparison with a newer, younger membrane. They're still relatively low compared to the 32 test, but it is higher than these results right here.
Thank you for saying that, because that's where I was going. So propane is a smaller gas than difluoromethane. Do we agree?
Mm-hmm.
So do you think that this is a size exclusivity separation, or does the fluorine group has something to do with it?
So it is partially size exclusivity, but also our membranes are fluorinated. So we also think that that has something to do, since the HFC 32 has fluorine molecules, but our membranes also have fluorine. There's sort of an interaction there.
Thank you.
Mm-hmm. Any other questions?
Dr. B.
So on slide 24, I was wondering, so you see this change in selectivity between the two solvents you used. So do you have any hypotheses on why you see such a high selectivity with the THF?
Well, one of the kind of biggest, I don't have a hypothesis right away, but one thing that we did notice in our different tests is that the THF membranes just were better overall. There was like, they were a more ideal size, and they were more consistent, they were flatter. And so I think physically, I think that has something to do with having a higher selectivity and having better permeability results. If we go back to the chemical composition of these two solvents, I don't have any like great answers right now on like how they could be different, but there is obviously some different functional groups on these solvents that could also contribute to the different permeabilities and therefore the different selectivities. I don't know if you have anything to add about that.
Great, thank you.
Thank you. Well, thank you all very much.
All right, our next speaker is Pritam, and he's going to talk about kinetic elucidation of a diffusion limited Suzuki-Miyaura coupling in anhydrous solvent, effects of an insoluble solid base.
Test. All right. Good evening. My name is Pritam, and I am part of the Dr. Algari Research Group, and my mentor is Tom Gonzalez. And today I will be covering kinetic elucidation of a diffusion-limited Suzuki-Miyaura cross-coupling reaction in an anhydrous solvent, the effects of an insoluble solid base. So we'll be going over some of the background, objective, and methods of our experimentations this semester, and then we're going to go over the results and end it off with conclusion and future work. And I'll thank some people and get out of here. All right. So what are Suzuki-Miyaura reactions? Well, they're used to form these selective carbon-carbon bonds in the synthesis of complex molecules, and they have a wide range of applications. Think like agrochemicals, pharmaceuticals, and even organic light-emitting diodes, which are used for like your iPad screens and your phone screens and whatnot. So they're all around us. Now, the objective of our research is to understand, is there mass transfer limitation in our specific SMC reaction, and what are the kinetics of the reaction? How will changing the aryl bromide concentration affect the reaction rate? And our reaction of interest involves this guy right here, which is our 4-bromo-biphenyl combined with our phenylboronic acid. And we utilize an expensive XPhos PDG2 catalyst with a solid potassium carbonate base. And we ultimately produce this guy called paratrophenyl. We hypothesize that if we were to use a solid base, that it's going to likely exhibit mass transport limitations, which is a phenomenon that creates these film layers around the solid base as the reaction proceeds, which ultimately kills the reaction. So what is the method of our experiments? What we do is we start with measuring out our CT vials, which is a very crucial step in understanding the mass balance of our reaction. And it's also where we put our aliquots of our samples. So we measure out about 39 CT vials, and then I go into the glove box where we prepare our reaction vials in an inert environment, preventing other side reactions. And here I add our reagents, which I previously mentioned, which involve our phenylboronic acid, our 4-bromo-biphenyl, and our catalyst in our reactor vials at 10 mils. And after that, I take it out of the glove box and I put it into our reactor where we set our conditions at 500 RPM with our stir bar rotating, and our temperature is at 50 degrees Celsius. Here we run the reactions for about 2 hours, and we take aliquots of samples throughout the entire time to monitor the reaction rate. And how do we do that? Well, we take it into our CT vials that we previously measured, and we centrifuge it to basically get like any ligands or any of the solid particles separated, and then we take another sample of that into our LC vials, where we put it into our high-performance liquid chromatography, which is our analytical tool. And this basically uses UV vis to detect the concentrations of each of our reagents as time proceeds. So how do we know like how much we made at each time? Well, we use these calibration standards at their specific unique lambda maxes, which is like their fingerprints. And that's how we know, like, hey, this is phenylboronic acid. This is our 4-bromo-biphenyl, etc. And through this, we are able to use Beer's law to calculate the concentrations at our specific times for each of our samples. And with this, we can get a lot of information like turnover frequency, turnover number, yield, conversion, etc., which is what I'll be going over today. So our first study involved our normal standard setup where we have aryl bromide as our limiting at 10 millimolar, and we have our phenylbronic acid at 16, which you can see right here. And the entire trend is that we have our 4-bromobiphenyl and phenylbronic acid slowly decrease, and our paratrophenyl, our product form. And we can see that the trend of the product form is a linear fashion. Now, it is a little bit scattered, but when we go into the 15 millimolar, we can also see that we start with the reagents at a more similar concentrations, and we see that the paratrophenyl yield is more linear. And if you were to give your attention right here, this is the concentration of our products, and this is the concentration of, I guess you can't see it. This is our concentrations of our reagents that we started with, and this is where our products are. And through this, we see that is a linear fashion of our paratrophenyl yield production. And then when we get into the 25 millimolar, we can see that it's actually almost like logarithmic, and we still see the similar trends of our reagents decreasing. So what can we conclude? Well, having higher aryl bromide or 4-bromobiphenyl concentrations, it ultimately increases our paratrophenyl yield. And this showcases that this is definitely plays a part in the reaction, as it impacts the paratrophenyl yield, and increasing the concentration increases the product. Our future work involves going from the glove box into a more shrink-blind system for future experimentations, and we want to continue testing the kinetics and monitor it by testing different variables such as temperature, the catalyst amount, and the base equivalence, and see how those play a role in the rate equation. I would like to thank Dr. Algier and my mentor, Tom Gonzalez, for all the support that they've given me, and the WISE program for hosting this event. I would now appreciate some questions. Yes? Yeah.
So I'm just wondering, how do you know when to stop in your calibration course? Because I see your points, like after concentration of 1, you only have 1 point, like which is 2. And then like you have like a lot of points, like basically in the 0 to 0.5 range. So I just was wondering, how do you know when to stop in your calibration curves?
That's a great question. So when we set up our calibration curves, we have different concentrations of each of our reagents going from 0.375 to 2 millimolar, and we just put them into our HPLC machine, and then that's how we can graph the absorbance versus the concentration. So your question about like when to stop, well, it only ranges from our 0.375 millimolar to 2 millimolar.
And if you go to your results, I want to see where your concentrations, like most of your concentrations are in the 20, from 8 to 20, I will say, like from 8 to 20, from 8 to 20 for 18. So like, but most of your point of your calibration curves are, you go back to calibration curves, your concentrations are only until 2, which I like, for me, it's kind of like so you are assuming that your calibration curve is straight until 20 concentration, and that's, I am correct?
Yeah, so this calibration curve.
Calibration curves are in a straight line until 20, and your concentration of 20?
Yeah, well, this is just to like monitor like the reagents throughout time. So this is our reactions setup where we have our 4-bromobiphenyl starting at 10 millimolar and our phenylbronic acid at 10. And this calibration curve is a method of basically showcasing the efficacy of our analytical method. So by seeing this, we have a retention time. Basically, when each of our reagents comes off the column, this is just to like detect like, hey, when I have this amount of absorption, I use this calibration curve to see how much concentration I have based on Beer's law. And I use that by utilizing the slope. But these concentration values are just showcasing how much of each reagent I have at that specific time. And I can give it off to Tom if you can explain that better.
Oh, okay. Yeah, but in that fact, like you are assuming that those are straight lines until. Oh, okay. Okay, okay. And have you ever seen saturation of, like, have you ever seen calibration curves that are not straight and they reach saturation or somehow they are not straight? They are not straight? No? Okay. Okay. Yeah, I'm just wondering, because I never use this, but I have worked in calibration course and I have seen saturation of the detector somehow. But yeah, but anyway, so yeah, good job. Okay.
All right, thank you. Thank you so much. I really appreciate it. You're awesome.
All right, so I'd like to introduce you the next group of speakers. Lauren, Elizabeth, and Celeste are going to talk about developing a reproducible drug delivery experiment for the chemical engineering curriculum. The floor is yours. Thank you.
Yes. Okay. Hello. Okay. Perfect.
All right, cool. So hi, I'm Elizabeth Aberle.
I'm Celeste Ruisinger.
And I'm Lauren Koskey, and today we're really excited to talk about a reproducible drug delivery experiment that is being implemented into the chemical engineering curriculum. So over the past couple of decades, there has been an increase in the interest for the pharma and biomedical engineering industries. The curriculum has been evolving, and so 1 or 2 biomed and pharma classes have been added into this curriculum. However, a hands-on experiment is also needed to supplement this learning for students. This experiment that we have designed is nice because it can be used within these chemical engineering classes, but also apply biomedical techniques and theories that are going to help students get their foot in the door for these industries. Within our experiment, we are using hydrogels. Hydrogels are polymeric substances that can hold and retain large amounts of water and liquids, which is why they're really nice to use in drug delivery systems. The hydrogels that we use specifically for this experiment are physical, meaning that they are impermanent, which is why our model drug is able to release into a system like a real drug does in a body. Hydrogels are very prominent in industry right now, which is also why it's so important to talk about them in our undergraduate degrees. They can be used in industry as contact lenses, wound dressings, they're used in tissue engineering, and then also in drug delivery systems.
So as we said earlier, we are focusing on more of the drug delivery applications of hydrogels. So kind of how we actually get to make these hydrogel beads. First, we're going to start off with our sodium alginate, and this mixture is also going to contain green food coloring, which acts as our model drug, so that we're then able to measure the release later. So when we have the sodium alginate, we're going to add it to our curing solution, which in this case is calcium chloride. We're going to let it sit for 1 minute, and this is what's going to form the physical bead walls of the hydrogel beads. Once we're done with that, we take it out and add it to a dissolution solution, which we're using water in this case. And as you can see at time 0, none of the food coloring has been released into the water yet. And over time, that green food coloring is going to diffuse through the hydrogel, physical cross-linked walls, and eventually it will turn the water green. And so that is kind of more on the physical visible scale. And so more on the molecular level, we can take a look at how those alginate strands eventually turn into the beads. So first we start with our singular alginate strands, and once you add it to that calcium chloride solution, it's going to go through an ion exchange with the calcium ions. That's going to eventually form an egg box dimer, and as this continues happening, it will form egg box multimers, which proceed to stack on each other, and then that is what will create our bead wall. So you want to take a closer look at that right image. You can see how that calcium ion is enclosed within those sodium walls, and that's what's going to give us our bead. So now we have to kind of figure out how we're going to characterize our beads and also create quantifiable data, which we can measure and then later on switch up different variables for. So how we're going to do this is we create a calibration curve, which is going to be measuring concentration versus absorbance. So for our concentration, we take different concentrations of green food coloring, add it into water, and then we're going to use spectrophotometry to measure the absorbance that aligns to each concentration. So as you can see, this forms a linear relationship, which demonstrates Beer's law, which is the linear relationship between concentration and absorbance. So as you can see, there's that really nice linear relationship, and by using this calibration curve, we're then able to create a control trial that we can use for further data gathering.
So the main thing we want to emphasize right now is that our experiment that we've developed is extremely reproducible between people. This is our release profile, and as you can see, all of our triplicates overlap over time, and all of our concentrations are the same at these times. So myself, Lauren, and Elizabeth all did a triplicate, and we all got very similar overlapping data, and this represents that we had so little error that we also could not use error bars, and this is extremely important in drug delivery because when a drug diffuses in the body, the release profile needs to be the same every time, so the drug is releasing the same every time within the body. So once we have this reproducible experiment, it's very important that we can also change variables so that we can test different theories. So the first variable that we changed is salinity. And as you can see here, we tested 5 molarity, 1 molarity, and 0 molarity of salinity in the dissolution solution. And this affects the release because a higher salinity solution causes quicker release within the drugs and a greater release. And this is because the drug beads are hydrophilic, and so the water inside the beads is attracted to the higher salinity solutions on the outside of the beads, and because the water is releasing at a greater rate, the food dye is also releasing at a greater rate. And then the next variable that we have decided to test is the initial sodium alginate concentration and how this affects the release. So in this experiment, we tested a 2 weight percent, a 1 weight percent, and a 0.5 weight percent concentration of sodium alginate in our beads. And as you can see here, the 2 weight percent sodium alginate did have the greatest release and thus the highest concentration over time. However, we do hypothesize that this is partially because within the 2 weight percent sodium alginate beads, there's also a higher concentration of food dye. And so with a higher concentration of food dye, you would also have a greater release because of this.
Finally, the last variable that was tested for this experiment is the bead diameter themselves. So there are 3 different methods that we use in the lab to create these beads, all of them producing a different diameter. This shows then some variability within your release. As you can see on this graph, the 0.3 centimeters, so the smallest beads, had the largest release over time and diffused the most into our dissolution solution. This is because your surface area to volume ratio is the smallest for those smaller beads, and as they get bigger, that ratio continues to grow, therefore stunting the release a little bit. However, it has been hypothesized within lab that if we were to create different sized beads using the same method, there would be some more variability and some more differentiation between all of these results. So in conclusion, this lab is great to have in an undergraduate curriculum for chemical engineering. It exposes students to the pharmaceutical and biotech industries while also giving a hands-on, safe, non-toxic, and reproducible lab. Due to the reproducibility, it's really nice for students to be able to do in lab and can be shown to be used multiple times. And then once you get your reproducible control trial done, you can change up your variables that you would like to see, which then furthers the theory that can be talked about in class. We'd like to say thank you to the wonderful company and its sponsors, and then Dr. Bertuccio and the Bertuccio Research Group. Thanks for your attention. We'd love to answer any questions.
Yeah, really nice presentation, and you know, the graphs and everything looked really, really nice.
Thank you.
I had a couple questions on these plots.
Yeah.
Is 0, 0, is it measured or is it just assumed?
Yeah, we do a blank, so just water in the cuvette, and that's where we get the 0 from within the spectrophotometer. Yes.
And then, so using the food dye is to simulate a drug. Do you know roughly about how large the food dye is, and is it similar in size to any drug that you might know of?
That's a really good question. I am unsure of that. That's not.
I'm not sure of like exactly anything like same size as other drug molecules, but for the time being, we just wanted something to represent like release. And we needed a simple molecule, green food coloring or any food coloring was really see it.
Okay.
Thank you.
And then that was a nice explanation about the size
Yeah.
of the beads, surface area to volume. Have you ever thought about maybe trying a different shape? I mean, the bead is probably spherical.
Yes.
Like, is it
Yes.
possible to make like a flat plate or some other shape other than just a sphere?
So that definitely could be possible, I think, with further experimentation. I know this lab is going in different ways, and I mean, that could be something that too could be implemented into a lab experiment for students to test. So it's definitely possible, yeah.
We did sort of like accidentally make different shapes at
Yes.
certain points,
There-
just using
yes.
like the different like dropper methods and like pump methods. But we just found that it was creating like such different shapes every time that there wasn't really a way to like measure the data in a way where we had like reproducible stuff just because it was making different shapes every time. But it definitely could be something in the future where we could make a shape that was constant with every trial.
Yeah.
And then most of your data is equilibrium data.
Mhm.
So have you done any experiments where you tried to measure the rate of dissolution of the dye into the solution?
Yeah, so I know others in the lab group have started to do that or have done that in the past, and that's something that I'm going to be doing like going forward with the research. But I know there has been experimentation done on that regarding the diffusion rates and all of that. So
Thanks.
yeah, thank you. Yeah.
May I ask why do you choose 60 minutes as the time of the limits the experiment? Because it looks like it goes to a plateau like after 60 minutes. And my second question will be, how do you know that you are in equilibrium? Like after 60 minutes, it looks like it will show a plateau, but how do you actually know that you are in equilibrium?
So the 60 minutes comes from just making this an experiment that can be done in class. So in like a lab setting, you're not sure how long a block time might be for a class. And then in regards to that plateau, so I've done experimentation where it goes to 90 minutes, you can do 120, whatever, and eventually your absorbance values that you're getting from your spectrophotometer just even out and plateau. So there's no more green food coloring really to be released into your solution. But the 60 minutes really just comes from making it an efficient lab that can be done in the curriculum.
Yeah, that's very interesting because actually if you see a plateau, it means like something will be actually be very, very stable at that point. So that comes to my next question. How do you know that you are in equilibrium?
That is, again, I think just when all the values are plateauing. So once you reach that state of there's nothing else really being able to be diffused and everything is in your system versus the things that aren't supposed to come out of your hydrogel are not, that's when you just reach your plateau. So if you were to hit 90 minutes and all of your values are the same, I think that's when you'd be able to.
There's a follow-up experiment that we're going to do. Take a mic, explain.
So there's a follow-up experiment that moving on in the next semester we'll do, which is to let those beads go for like a day or a week, just to see like what is the true plateau, so we can feel a lot more confident at like 60 or 90 minutes that, yeah, we've pretty much hit equilibrium at the 60-minute mark.
This plot right here shows us the different weight percent. And I understand you have ways to make beads bigger or smaller, Does the weight percent affect the size of the bead when it hits the solution?
No.
Yeah. No, the method that we use is the pump method. So all of our beads are being pumped at the same rate from the same height. And so even with varying weight percents, because of the pump, all of our beads end up being really, really close to the same size.
Yeah, and then as they go through the system, I've noticed in mine, as you get to those higher weight percents, I mean, they're just gonna get smaller faster because they're diffusing faster throughout your 60 minutes compared to maybe the 0.5 weight percent. But I mean, that original size is the same, and then depending on their end result, that's gonna kind of dictate the end size of your bead.
Yeah. And just a basic question, when you start each experiment, how do you determine the amount of beads at time 0? Is it weighing? Is it counting? Is it?
Yes, it's weighing. So we have a standardized weight that we use, 3 grams, that we use each time, and that kind of makes it so that each experiment is gonna run the same, and you're having the same amount of beads or the same weight being put into your solutions.
And when you weigh them out, it's like a little squishy beads,
Yeah,
right?
yeah.
So they're wet with water, but I guess it's obviously very reproducible.
Yeah.
So you just pull them out.
We do dry the beads.
So yeah, when you
also.
take them out of your curing solution, you're drying them and rinsing them before you're putting them onto your scale to be able to evenly put those into the solutions.
Well, I really enjoyed your talk. You just mentioned an answer that piqued my interest. So does the bead actually shrink? It does?
Yes.
Okay.
Yeah.
That's fascinating.
Yeah.
If you watched Pritam Ray's presentation,
Yeah.
that's the shrinking core model, like an application with a pharmaceutical reaction. And my second question is, it has to do with the number of bead particles when you weigh them. Do you track the number of bead particles that you produce? I mean, can you count them while you're doing this? And
Yeah.
the reason why I ask that is, so if you have a variance in the number of particles, but you target the weight, that means the particle size, it's got to be a little bit different.
To a certain extent, yes. Because our results are so reproducible, I think that kind of can demonstrate that it's not variant enough to really matter being negligible in this case. Yeah, we're testing for weight. We're trying to just get a same weight going into it every time. But because our pump method is so standardized and creating the exact same bead every time, the size is not really important then at that point.
It'd be kind of fun if you could just change the diameter on that, on your bead producer.
Yeah, the pump.
And the thing is, Dr. Shiflett suggested like have a different shape, but maybe add stirring to it, do some Sherwood's calculations, validate your diffusivities, like those sound like a lot of fun.
Yeah, it's really cool.
Yeah, and that's kind of something we're looking into in the future too, is obviously when we talked about the bead diameter sizes, those were all from different methods of like creating the beads. So we use like a dropper method, like a pump method. And so in the future, we're kind of looking at creating different diameters from just that pump. So they're still really reproducible, but we can test out the different sizes as well.
Yeah, thank you. Thank you. All right, thank you guys.
Thank you.
Thank you.
So up next is Kiersten Aris, and she's going to talk about the impact of storage environment on the chemical and mechanical stability of alginate beads. The floor is yours.
All right, hi everyone. As you were just told, my name is Kiersten, and I'm here to share with you my research about the impact of storage environment on the chemical and mechanical stability of hydrogels as a drug delivery system.
So the price you pay for your consumer or your pharmaceutical products is directly related to a variety of factors. What I focus on is the cost due to storage and transportation. So every year, billions of dollars are spent on the transportation of pharmaceutical products. And that is the cost of transport is the result of, again, a variety of factors, some of which include temperature. The colder you have to store your products, the more it'll cost because you have like all the refrigerants that you need in order to keep those cold. So if we can keep pharmaceutical products at storage temperature, it is a lot cheaper. An additional factor is weight. So the lighter your pharmaceutical products, the less expensive it'll be to transport them. Now, a lot of pharmaceutical products are protected via encapsulation. And an up-and-coming method for encapsulation is the use of hydrogels. Now, hydrogels are polymers that are really good at holding onto water. And we can assume that because they're good at holding onto water, they'll also be good at holding other compounds, such as hydrophilic drugs. So the drugs will be suspended in the gel and then be encapsulated through the gelation process. The hydrogel we use is alginate, and it is really cool because it's naturally derived from brown seaweed, which means that it's biodegradable, biocompatible, non-toxic. It's also sustainable, and most importantly for us, it's inexpensive, both in acquisition and processing. So in my experimentation, again, I'm storing my drugs under various conditions. But in order to create my beads, I'm encapsulating green food coloring as my model drug using a method we have termed the pump method. Our pump is pumping our alginate mixture at a constant speed and then utilizing gravity to create evenly sized spherical beads. I then store my beads in various conditions. From your left to the right, I either freeze my beads, store them in wet solution with green food coloring at a higher concentration than what's in the beads, or dried. And they're stored in those conditions for a period of time. After this period of time has elapsed, I directly put my beads into the dissolution solution and measure the change in concentration over time using spectrophotometry. The standard experiment is to create the beads and then immediately put them into the dissolution solution. My graph here represents the change in concentration over time. It's valuable to note that it looks like the concentration increases faster at the beginning than it does at the end, meaning that it begins to plateau. And this is due to the decrease in the difference in concentration. So the higher the concentration gradient, the more or the faster the solute will move from one side to the other. After I had established my primary experiment, I switched to testing different storage conditions, and the first of which was frozen. Now, as you can see, all my data points are at 0, and this is because I didn't have any food coloring dissolute. However, this is not because alginate doesn't allow my beads or does not allow the green food coloring to dilute out of the beads. It's because when we froze our beads, the water crystallized and made our beads explode, which means that all my food coloring exploded out of my beads too. Now, despite the setback, I continued with more storage conditions, being wet storage and dry storage. What's interesting is that these performed in a similar manner. This demonstrates that the release behavior is a spectrum, so our storage environment definitely does play a role in how much green food coloring can be released from our beads. And although the dry and the wet storage is very different, they performed in a similar manner. And although I don't know exactly why, I have some hypotheses that I'd love to talk about during my Q&A section. So yeah, as I said, the storage environment does play a role in the performance of our beads. And this is important to us because it means that alginate has the flexibility to meet the needs of whatever product it is encapsulating and also meet the needs of the company so that we can minimize cost. So yeah, alginate is, or just hydrogels in general, are a really cool up-and-coming method for encapsulation. And because we know that alginate is good at demonstrating the release behavior, in the future we can use this to recognize the release behavior of other hydrogels that will be used in drug delivery for real. And I would just like to give a thank you to the wonderful company, as well as my research advisor, Dr. Bertuccio, and the rest of the Bertuccio group. So, anybody have any questions?
Hey, thank you for the talk. I was curious, what was the freezing process?
So I produced my beads via the pump method. I dried them and then put them on a plastic tray and put them directly into the freezer. So there was no like constant to cold. It was just like room temp to freezing.
That kind of leads into my question. Do you think like a gradual freezing process might work a little better?
Yeah, I think that is definitely something we should pursue. But as I was talking about earlier, it costs a lot more to transport cold things. So if we are able to store these products at room temperature, that would be more fiscally advantageous, especially since hydrogel is already inexpensive to begin with. It makes it more accessible for global like drug distribution.
Thank you.
Just as a follow-up question, how is the wet process? Like, how do you get those wet?
The wet process. So I make my beads as normal, and then I store the 4 grams of beads in 10 milliliters of water with a higher concentration of green food coloring than what I used in the beads. So the goal is that if anything, the food coloring will go into the bead instead of out. However, we don't believe this is what's actually happening because the beads are reduced in weight throughout the storage process, meaning that water and in conjunction, the food coloring are diluting from the bead during the storage period.
And everything is at room temperature?
Yes, everything but the frozen beads.
Okay, thank you.
In the beginning, when you talked about transport and you talked about transporting under refrigerated conditions versus room temperature. So we had a graduate student, Nicole Montoya, and this was her master's thesis. And so she was working on developing porous materials where the pore size was kind of just the right size for the active ingredient in the drug, which in this case was a protein. And so the protein could go into the pore and bind with the pore wall, and that would prevent the protein from denaturing when it warmed up. And so we've showed that that potentially is possible. So if you're interested in that, it's not a very long thesis, it's maybe a couple hundred pages, but if you're interested, we can get that to you.
Yeah, that's really interesting. Actually, there's research that hydrogels have been used to protect biologics. And because they are physically cross-linked, we can just add sugars to them and they can be injected. So it's really cool.
Why the dry and the wet are the same?
Yeah, so first on the dry, the water evaporates out of the beads, which condenses the matrix of the polymer. And so we are assuming it's more difficult for the green food dye to dissolute from the bead. And then, as I mentioned previously with the wet beads, they reduce in size throughout the storage process. I think it's from 4 grams to 2 grams, which we assume is the result of both water and food coloring leaving the bead itself, which means that there's less food coloring to dissolute at the beginning of the release period.
Interesting.
Can you go to your future work slide?
I don't have
Oh,
one.
you don't?
No.
What would you think would be a next great step since you've evaluated kind of a structural integrity of your hydrogel? Like,
Yeah, so I've begun working on how I've begun using other model drugs, being other food dyes, to evaluate how molecular size and hydrophobicity impacts the rate of diffusion, and then also how that is impacted by storage.
cool. Maybe even examine like treatment of the hydrogel material, like the polymeric material outside, and then maybe like examining not just the alginate, but other sources like bananas or other ways of getting these kind of hydrogel materials. Be kinda cool.
Definitely.
Well, we're doing a great job. We're actually running 2 minutes ahead of schedule. So we have 5 more presentations to go. And the next presentation is Evan Dennard and Carson Wellbrock. And they'll be talking about separating R410A refrigerants using MFI zeolites.
All right, well, hello. Good evening, everyone. My name is Evan Dennard.
Carson Wellbrock.
And as Dr. Shiflett said, we'll be discussing for our research project the separation of refrigerants using MFI zeolites. All right, so here's just a bit of an itinerary for this evening of our presentation. All right. So first, we'll go into a little bit of history of the refrigerants. So the first mixtures, or not mixtures necessarily, but first refrigerants were created in the mid-1800s, and back in those days, they pretty much would have just used whatever compounds that were known at the time that had the right properties for being refrigerants, such as ammonia and sulfur dioxide. However, those systems were very toxic and prone to leaking, so those had to be phased out eventually in the 1930s and replaced with CFCs. However, eventually, by the 1980s, it was very known that CFCs were damaging the ozone layer by disrupting chemical reactions that occur there. So therefore, HFC refrigerants were created as a replacement in the 1980s to phase out the CFC systems. However, eventually, we arrive where we are today, where HFCs are needing to be phased out due to environmental concerns regarding climate change and the global warming potential of the HFC compounds being very significantly high. And therefore, those need to be replaced with HFOs, or hydrofluoroolefins, or HFOs mixed with HFCs in order to obtain the right thermodynamic properties for the mixtures. So here we have a bit of a diagram here, or I guess picture, showing an HFO and an HFC, a bit of the structural difference. So in this slide, we basically just have a visual representation of what I talked about earlier, how one generation of refrigerants will have one generation will be introduced to solve a problem of the previous one. However, that one will then have its own set of problems and therefore need to be phased out and recycled in an environmentally friendly manner. However, most refrigerant mixtures, since They are azeotropes, meaning they have very similar boiling points. They can't really be separated by a very simple method such as distillation. And in order to be recycled, they have to be separated. So that brings us into what we're researching here, which is how zeolites can be used to do that. So zeolites are these aluminosilicate molecules that have a porous channels and structures, as you can see in the pictures down here. And one of the naming factors of them is the silica to alumina ratio, as well as the structure of the framework that you see. Another factor is calcination temperatures. And there's also within the, calcination is done in order to remove impurities. And then within the structure also are many cations, such as H+, which are in order to keep it electronegatively neutral and stable. So our objective here at the Shiflet group is basically to determine the optimal conditions for separating this refrigerant mixture here, this common mixture R410A, into its individual components again, in order for those to be recycled, and that the mixture is 50% HFC32 and 50% HFC125 by its weight. However, as mentioned earlier, we can't really do that using a simple method such as distillation. However, what we're investigating is, or I guess researching, is a better term, is how to use MFI zeolites in order to separate that back into its individual components as effectively as we can in order to recycle as much HFC32 as we can, or collect as much to be recycled. And the silica to alumina ratio, and as well as to a lesser extent the calcination temperature, will determine the selectivity of zeolites towards a specific refrigerant. So then here's a little bit more about the selectivity. So we have some of the silica to alumina ratio of the zeolites that we're testing, as well as some of the calcination temperatures that they're being tested at. And as mentioned earlier, the zeolites are these molecular sieves that absorb the refrigerants in their pores. And also in this diagram, you can see here some of the channels that are located within the zeolites. So we have some here, and then if we rotate it 90 degrees, we can see different ones at a certain angle. And because of the silica alumina ratio and also those temperatures, the zeolites will have a stronger selectivity towards HFC 125 than 32, which is what we wanted to have. So I'll pass it off to you now.
All right. You guys hear me all right? Good? All right. And this is our procedure. So on this left image, you'll see the breakthrough apparatus we used to conduct our experiments. And then on the right, we have kind of a simplified block flow diagram to explain our process. So what we do is we flow R410A through our system, through a mass flow controller, so we know exactly what goes into our system. And from there, it'll go into a bed packed with zeolite, and then it'll come out eventually through the mass flow meter, the mass spectrometer, and then onto the computer, where we see exactly what comes out, its composition, and the rates that it's coming out. And then from there, we can create a breakthrough curve to analyze our data and come to some conclusions. And here's what we found. So this graph on the left here, we see the green horizontal line and the red horizontal line are going to be our HFC 32 and 125 coming into the system. And then the black line is HFC 32 coming out of the system, and then the dotted red line is HFC 125 coming out of the system. And as you'll notice, during the first 30 minutes of our experiment, no HFC 32 or 125 comes out of our system. That's because our system is absorbing both the 125 and the 32, and so nothing's being released. And then shortly after the 30-minute mark, there's a substantial breakthrough in 32 coming out of our system, and that breakthrough goes above even what our feed is, so we're getting out more than what we're putting in at a given time. And the reason for that is the 125 is coming into our zeolite and replacing the 32, essentially kicking it out of the system, because the zeolite is more selective towards the 125. And then eventually, shortly after 40 minutes, we see the breakthrough of HFC 125, and this represents our zeolite being completely saturated And then our levels eventually plateau and reach a state where everything coming into the system comes out. And then on the right, we have a comparison between our calcination temperatures, our SAR, and the selectivity of a zeolite. So as you'll see, that bottom blue line is an SAR of 30, and then the line above it, the orange one, has an SAR of 150. That is a very noticeable jump in selectivity, much greater than the change we see when we change calcination temperature. But regardless, both of them have a positive correlation, and we can use those to adjust the selectivity of our zeolite. So through our experimentation, we found that MFI zeolites can be used to separate refrigerant mixtures into their individual components. In our case, this was R410A into HFC 125 and HFC 32. We also found that we can manipulate the selectivity of a zeolite by changing the SAR or the calcination temperature. And in the future, we plan to explore how other zeolites or other porous materials, maybe something like activated carbon, could be used to improve the efficacy of our refrigerant mixture separations. And that's all we had today. We'd like to thank Emmanuel Ababio, Dr. Corbin, Professor Shiflett, Andrew, and our Earth colleagues. And that's all we have. Have any questions? Oh.
Thank you for a really nice presentation.
Thank you.
Thank you.
I really like that your experimental apparatus has this mass flow meter at the end. And so can you tell us, like you had that one graph that had like millimoles per minute or millimoles per time. Yeah, this thing. So can you tell me how you calculate it? I assume you have to use something that comes from the mass flow meter, do you?
So a lot of our calculations were done by a manual. And so I think he would have a better understanding of how exactly the calculations work for our system.
So the calculation is just we just try to determine the mole fraction of the species. So we just move by determining like move instead of grams, we convert it to moles. Yeah.
So you need to determine the mole fraction. You get the mole fraction from the mass spec?
Just first off, we determine this moles from the peaks that we get from the mass spec.
Yep.
That's what we use to determine that. It's just a bunch of calculations where we have to go through processes to get the RSFs and all that to get the calculation. It's really a long calculation.
Okay.
Yeah.
All right.
Anyone else?
I could ask another one. So these on the right, you show us 3 different materials.
Correct, 3 different zeolites.
Yeah, those materials were loaded at the same mass or the same volume, or they end up being both the same?
It would be the same volume. So they're in the same bed, and the bed's the same size.
Oh, I was thinking, like, should we go back to the picture with the actual, like,
Oh yeah, we can
apparatus?
show it on the apparatus. So you see the creamish color insulation.
Sorry, I'm colorblind.
Oh, well,
True story.
it's
not
got
a
a
lie.
bunch of, like, this insulation you don't see, it's like wrapped around a bunch of times.
And that's our bed, so it's the
Sure.
same volume.
Yeah. So is there anything that you have to be careful of if it was the same volume versus the same mass? Does it end up being pretty close to the same mass?
I think for the zeolites we tested, they were all similar in mass, but if we tried other zeolites, that would definitely be something we'd have to look out for.
Thank you.
Well, you just mentioned that the system is have higher selectivity for HSC 125 than HSC 32, as you see in the next picture, as you have shown in the next picture. So why the system shows higher selectivity for HSC 125 because of the zeolite that they use? Do you know if there is another one that it will have higher selectivity of HSC 32, and why is it easier to capture HSC 125? Why is not like in the opposite? Why now the zeolite have more affinity for HSC 32? I'm just wondering. It's just.
I personally don't know like molecularly why it captures. So what we were testing was the silica to alumina ratio. And what we found is that the higher the silica to alumina ratio, the more selective it was towards 125. So I guess if we went the other way, we could find a zeolite that's more selective towards HFC 32.
But our goal is to get as much HFC 32 out as we can and as little, we want to absorb as much HFC 125 as possible in order to separate the mixture.
Yeah, true. I guess it doesn't matter which is more, which of them have more affinity by the zeolite. And in terms of purity, do you know like how well is the separation? Did you calculate that, or do you have an idea how well is the separation with this zeolite?
I remember seeing purity numbers, but I don't remember exactly what they were. Yeah. Thank you.
Great, thank you.
No, Emmanuel?
So we expect pure HFC 32 to come out from the bed. Yeah, we get more than 99. Yeah, 0.5. Yeah, 0.5%. We get more, yeah. And about the question that you asked first, which concerns why this MFI zeolite separate kind of have high selectivity towards HFC 125 than the HFC 32. Yeah, we attribute that to the kind of the size of the pores because of the channel. Because when you look at it, it's the HFC 125 is having about 4.4 angstroms its size, kinetic diameter, and the MFI zeolites that we use, they are having diameter of between 5.1 to 6 angstrom. So there's that kind of strong interaction between the HFC 125 than the HFC 132. And also the HFC 32 is more polar than the HFC 125. So we expect that as we increase the silica to alumina ratio, it becomes more hydrophobic. Yeah.
Anyone else?
Okay, hi everyone, I'm Lily and I'm going to be talking about factors that affect the model drug release from sodium alginate beads. So over the past few decades, there's been an increase in need for chemical engineers in the biotechnology and pharmaceutical industries. And this has called for a lot of schools around the country to start modifying their curriculum in order to include 1 or 2 bio-focused courses that include drug delivery, biotechnology, anything in that biotech and pharma industry. So what we've done in this case is created a hands-on experiment that can be done in a shorter time frame in order to start educating undergraduate chemical engineers in what a possible career in the biotech industry could look like, as drug delivery is the process used to deliver a drug to a specific area. And in this case, our drug is green food coloring encapsulated in a sodium alginate bead. So the way we're creating these alginate beads is by the pump method, which is where we use a pump to dispense sodium alginate gel into a calcium chloride solution, where it is cured for 1 minute before taken out, dried, and then put into a dissolution solution. So we measure the rate of release once it's in the dissolution solution every 10 minutes for 60 minutes. And as you can see here, the beads before they're placed in the dissolution solution look like they're very full of our model drug, the green food coloring, but then after 60 minutes, after we measure every 10 minutes using a spectrophotometer, you can see that a lot of the model drug has escaped the beads, and the beads all look a lot lighter. So the way that this bead wall is formed that encapsulates our model drug is by a cation exchange between sodium and calcium. So what happens is those calcium ions come together with those alginate strands and create the calcium alginate hydrogels. And then many of those calcium alginate hydrogels come together to create this cross-linked polymer network, which is called the egg box model. So that's a little bit behind how the sodium alginate beads are actually formed and how that model drug is kept within the bead. So then once we established how to make our beads, we decided to start testing a couple different variables. So the first variable I tested was changing the concentration of the calcium chloride curing solution. And what we found is that increasing the concentration of the calcium chloride solution increases the rate of release, whereas decreasing the concentration of the calcium chloride solution also decreases the rate of release. This is a little bit different than what I had originally anticipated when I started doing the experiments. I had thought that the smaller concentration of the calcium chloride solution would create a higher release, but that was not the case. We still aren't 100% sure what's happening in this case, but what we hypothesize is that that super high molarity of calcium chloride, the 5 molar, that bead wall on the outside is forming so quickly that it's not able to get past that, meaning that the sodium alginate gel within the bead is still more liquefied than that of the beads that were cured in the lower molarity calcium chloride solution, where the sodium alginate gel inside the bead has become a lot more viscous and isn't escaping as easily. After we tested the calcium chloride curing solution, we decided to test different dissolution solutions. And we tested a pH of 13 dissolution solution, which was sodium hydroxide, as well as a pH of 1, which is hydrochloric acid. And what we found in this case is that the more basic solution caused a higher release rate, whereas the more acidic solution caused a much lower release rate. And what's happening here is that basic solution is causing the sodium alginate to swell up and start to dissolve, making that model drug able to escape the wall at a much higher rate. And that acidic solution is causing the bead to shrink and stay intact, meaning that our model drug is escaping at a much more slow rate. And so overall, we found that the composition of the dissolution solution can affect the rate of release from the alginate beads. Like we saw that a more basic solution will cause a higher release rate, whereas a more acidic solution causes a slower release rate. We also found that the concentration of calcium chloride curing solution also can have an effect on our rate of release. We found once again that a higher concentration of curing solution causes a higher release from our sodium alginate beads, whereas a lower concentration causes a slower rate of release. And overall, this is a very good hands-on drug delivery experiment to start incorporating into the chemical engineering curriculum. It is very safe, non-toxic, affordable, and can be completed within a 2-hour time frame. Okay, and I would like to thank WISE and Dr. V and the Reproducible Research Group. We have a wonderful holiday party picture right here. Yeah, thank you. And I'm happy to answer any questions.
Thank you for a nice presentation. So I really want to thank you because you had a result that you didn't understand, and then you came up with a hypothesis, and that's research. That's wonderful. It doesn't always happen at the undergraduate research level. I think it's fantastic. And I understood what you were saying. Are there any ways that you can try to support your hypothesis? How big is a bead? Is it millimeters or is it centimeter? Or?
We usually measured it in centimeters, and yeah, I believe with the pump method, it was around 0.2 or 0.3 centimeters for each bead in diameter.
Okay, 0.2 centimeters. And so, do you ever think about microscopy? Like you could actually cut one of those in half probably.
Yes, I think so. But as far as my prediction for the calcium chloride curing solution, I'm trying to think of something that would help test that. I would say maybe something we're looking forward to in the future is trying to quantify how much food coloring is in each bead, and maybe discovering that would see, I guess, I don't know. Definitely something to look into, but yeah.
I also was going to suggest we also need to look at like the structure of our bead and like how squishy it is.
Yes, yeah. An interesting thing about that was we found that when testing our pH, we found that when we put the beads in a more basic solution, they were a lot squishier than when we put the beads into an acidic solution. So that's another thing to look into in the future.
When you're putting it in a more basic solution, you're using sodium hydroxide. So the material you're starting with was sodium alginate, right?
Yes.
So the calcium that you put in helps cross-link it and makes it stronger. So when you're putting in that base, you might be re-exchanging that calcium with sodium back again. So it's getting weaker. So that could be why that's happening.
Okay, awesome. Okay, thank you.
So our next speakers are Abby Peters and Carly Barlows, and the title of their presentation is Adsorption and Desorption of PFAS on Zeolite.
Hello, my name is Abby. My name is Carly. And so we work with CJ on Project Discover for the absorption and desorption of PFAS onto zeolites. So PFAS are per and polyfluoroalkyl substances or fluorinated carbon chains. It's a large group of chemicals with varying chain sizes and functional groups. But of primary concern for us are PFOS and PFOA. These are the most widely used and widespread PFAS, and of the primary concern for the EPA regulations around drinking water treatment plants. So PFAS are pretty widespread within the environment, including our water. They're widespread and found in all major water sources throughout the world, especially like our groundwater, our surface water, and even our water post-treatment at drinking water facilities. So especially like in Lawrence, we have PFAS within our drinking water. We have some elevated levels of PFBA. But in comparison to places like Leavenworth, which is a military base that have really high levels of PFAS, Lawrence is pretty safe, but it's still of concern. So currently, drinking water treatment plants have a couple different methods of PFAS treatment. In terms of adsorption, they use granulated activated carbon or ion exchange resins within packed bed systems. So both of these are able to be regenerated. However, that's not always the primary practice, and nor is it efficient or available. So for example, GAC is often thermally regenerated, but these thermal regeneration sites are pretty specific. They have to be to a certain code, so it's not always done in-house. And these sites are found usually around the coast. Texas is where the primary ones are, so it's not always easy to ship these off in large amounts to be thermally regenerated. Additionally, like ion exchange is pretty environmentally taxing to produce, so you want it to be regenerable, but it also sometimes cannot be done in-house. So these systems to regenerate are somewhat difficult, not always done. And also with these materials, they're not super selective towards PFAS, so they interact with a lot of different components within your water matrices, which means that you're going to have a shorter bed life whenever you're looking at PFAS absorption. This means that you'll have more frequent regeneration or replacement, which leads to extra cost. Additionally, GAC and anion exchange can cause issues with your water post-treatment, such as heavy metal leaching or corrosivity. So we're looking at zeolites, which we talked about a little bit before, but they're molecular sieves. And so we've worked with them to do some absorption experiments in the past. And now we're kind of at the stage of characterization and optimization of the zeolites and also the regeneration work. So we've been focused on CP814E. It's a beta zeolite, and we're looking at the hydrogen form. However, zeolites are really able to be modified to optimize the selectivity for PFAS. So we've worked with dealumination and exchange with the different metals, and we've also worked with ion exchange.
Okay, getting into some of the experiments we've ran this semester. Like Abby said, to be able to characterize our zeolites, we use a machine called the Igosorb. And what this does is help measures the water absorption of our zeolites, or the hydrophobicity of our zeolites. And it does this by directly measuring the relative humidity versus the weight. This is a simple schematic I made where the dry nitrogen can go in and help the sample reach a 0% relative humidity. And as we want to increase the relative humidity, it goes through a water solvent, and it reaches the sample that is hanging in a stainless steel mesh basket that allows for the gas to flow through it easily. The water bath is temperature controlled, or controls the temperature of the system. Our scale actually accounts for buoyancy as well, which is important for our experiment because we want to make sure that the weight change is only due to the sample and not due to other factors from the change in relative humidity. The two zeolites that we're testing are hydrogen beta and calcium beta, beta meaning the large pores within the framework of the zeolite. The two PFAS we're testing are PFOAs and PFOS because they are the most regulated. Okay, getting into some of our results. So this is a weight percent versus relative humidity graph. So first comparing the hydrogen beta and the calcium beta, or the red and the green points. You can see that they more closely follow each other at lower relative humidity. However, at higher relative humidity, the hydrogen beta starts to deviate a little more, or gets more hydrophilic, meaning it absorbs more water. On the other hand, the calcium beta absorbs less water, meaning it's more hydrophobic. And this is what we prefer to see in a zeolite because the hydrophobic nature of it better interacts with the PFAS and more easily removes it. And once we determine that calcium beta is the better zeolite for our purpose, we tested it before and after regeneration. So the green points compared to the blue and the black points. We see that they more closely follow each other at a lower relative humidity. However, at about 40% relative humidity, they start to deviate a little bit. The regeneration samples get higher in their weight percent, meaning they're absorbing more water. We're still trying to figure out why this is happening and are running more characterization tests because theoretically they should be following the same curve before and after regeneration. Okay, another set of experiments we've been running is with the ICP. And what this does is detects and quantifies our elements of interest. And for us, that is silicon, aluminum, calcium, and sodium, because those are the main elements found in the zeolites we use. We want to be able to confirm the ratio of silicon to aluminum added to be able to make sure that the framework within our zeolites is what we expect. Before we can run any samples, though, we must digest our samples within the mixture of nitric acid, HCl, ammonium fluoride, and boric acid. And what this does is dissolves our zeolites into their ionic forms, so the metals within them can be more easily traced and picked up by the ICP. And this is a picture of the ICP. Okay, and getting into some of the results. This is our calibration curves of concentration versus the intensity. So the linearity within the curves means that the concentration is what we expected. So for aluminum, sodium, and silicon, they are all perfectly linear, meaning the concentrations are what we expected to see. However, the calcium curve is a little bit less linear, which tells us that there is some source of calcium contamination within our runs. So we have tested the water that we're running, or that we're using within our experiments. We've tested all the acids, and we've tested the zeolites, and ruled those out as the sources of calcium contamination. So currently we are thinking that the source is from the plastic bottles we're testing our samples in. So we are currently soaking them in a nitric acid bath with water and nitric acid to hopefully reduce the calcium contamination. Since the silicon and aluminum were not affected by this, we're able to compare their ratios within the zeolites. They should be expected between 12 and 13, and their averages give exactly that because the zeolite manufacturer says that they should be around 12.5. The majority of our work this semester has been with the supercritical carbon dioxide reactor, which we know that carbon dioxide reaches supercritical at a temperature of 31.1 Celsius and 1045 psi. We've been varying the temperatures and pressures to see which works best with our system, and we've also added nitric acid into our system at different concentrations to see which one best works. The reason we're using supercritical carbon dioxide is because we want to determine if our zeolites can be regenerated on site for drinking water treatment. We know currently that methanol is a good way of being regenerated. However, they are not good for drinking water treatment facilities. On the other hand, supercritical carbon dioxide is an approved solvent. So there's already work being published covering supercritical carbon dioxide and PFAS desorption with additives like sulfuric acid or nitric acid. So these are some examples of published work showing that methanol and supercritical carbon dioxide are good ways of removing PFAS.
So in conclusion, we were able to confirm that our calcium beta is more hydrophobic than our hydrogen beta, even after thermal regeneration. Our ICP has allowed us to confirm our silicon aluminum ratio as well within the expected range. And we're continuing the work with the calcium ratio to overcome the calcium contamination. And then we're also continuing to get results with our supercritical carbon dioxide reactor in terms of regeneration of zeolites post absorption of PFAS. And so in the future, we'll continue with the ICP work for the digested zeolite samples post-supercritical, as well as the thermally regenerated zeolite samples. And then we'll continue our work with the supercritical reactor with our ion exchange zeolites and granulated activated carbon. So we'd like to thank Dr. Shiflett, CJ, Dr. Corbin, and Dan for their help with this project. And thank you. Any questions? Okay. Yeah.
Thank you for your presentation. Supercritical CO2 is interesting. I guess the idea is to dissolve them off. Is anybody thinking about using a fluorinated solvent to dissolve them, like even the R32 or something else? It might be a liquid at milder conditions than CO2. You ever see that in the literature?
So I haven't looked at fluorinated substances specifically. How we chose supercritical is that it was the most like PFAS in terms of the available solvents or approved solvents that can be treated in-house at drinking water treatment plants. So that's kind of the list that we're working off of first. It's really hard to get solvents approved for drinking water treatment facilities.
Yeah, that makes sense. Yeah.
But yeah, so that's
probably
how we
my
chose.
suggestion is not approved for.
Probably.
I have another question. This Igazorb experiment showed you that the H beta, right? H beta was more hydrophilic. Do you have a thought about why it is more hydrophilic?
Wait, can we go back to it? Well, we know that hydrogen has a lower positive charge than calcium beta does, so this could be due to the fact. And we know that the calcium beta will better interact Actually, sorry, I'm
Okay.
I think we're not totally sure why this is the way it is. It just, zeolites are funky things anyways. So I think we're still working on
I was
figuring out why.
wondering if calcium is actually kind of big. Well, it is big compared to H.
If it's pore blocking the water.
Either pore blocking or maybe just there's not as much pore volume. So is the pore volume of H and calcium beta similar? Has it been measured?
So those, CJ's primarily working on that with BET,
Sure.
flowing with argon. So unfortunately, we don't see that part. So that's
Are they
probably
different?
a CJ question.
Yeah. Sure. Okay. Thanks.
So I had a quick question about, so you mentioned you got this weight percent on a dry basis. So I'm curious, like, can you put in perspective to me, like, how much does like one weight percent matter, or like how big of a difference it is?
quite sure. CJ might know.
So it's more relevant as a comparison because we're using water. The relative humidity in water is 100%. So we're using this as a comparison to say, okay, well, at conditions where we can actually see how much water there is, does it like water more or less? And essentially, what we think that this is saying is this is probably one part of the reason that we see better absorption of calcium exchange forms. It's probably not the entire.
Thanks.
I don't think it's on.
1, 2. Now I think it's on. Is ethanol an approved solvent? No? Okay. I figured because you can drink it maybe.
Yeah.
And the other one is in your desorption tests. Can you go back to your drawing? Yes, this looks very nice.
Thanks.
So you add your zeolites to the vessel?
So we add the zeolites. So the zeolites have PFAS on them, and then we put them in our stirring. So that stirred basket up there to the right top photo is a stirring basket. So we put the zeolite in there. There's 2 micron frits on either side, so the zeolite can't get out. Most of the zeolite can't get out. It's mostly larger than 2 microns, but the PFAS and the supercritical carbon dioxide and other additives can flow in and out of the system. So it's in the basket stirring within our PAR reactor, and the PAR reactor is closed system. So right now we're running them as batch, but hoping to move towards more like continuous flow systems.
Yeah, that's actually what I was about to suggest. Just like maybe a bed would work best if you're trying to take something out than a batch reactor. You're probably thinking about those, but there are those back. I don't remember how they are called, but there's those valves that keep constant pressure when you have flowing. So you might want to use one.
Yeah, that's a good suggestion. Thank you.
Back pressure regulators.
Okay. Any other questions? Thank you.
So our next speakers are Elenore Broderick and Matthew Goodman, and the title of their presentation is Tuning the Synthesis Process of Sodium Alginate Hydrogel Beads with Encapsulated Magnetic Particles to Model Drug Release.
Hi, my name is Elenore Broderick.
And my name is Matthew Goodman.
We're here today with Dr. Bertuccio's drug delivery group to talk about our sodium alginate beads that we encapsulated with magnetic particles so that we might see how they would affect our drug release.
So the overall appeal of hydrogels is, first of all, it's biocompatible. This means that it is non-toxic to the human body and makes it very useful for things such as encapsulation for medicines. Another reason for it is it's a cheaper alternative to other encapsulation medicines, making it very appealing for industries such as pharma. And it's environmentally friendly through its biodegradability, so you don't have to worry about adverse effects towards dumping it as a waste product. Also, because of its non-reactivity with other different particles, you can really utilize it with metals and medicinal factors to utilize their properties without worrying with adverse effects of the sodium alginate being applied to it. Another reason is it is very easy to produce, only requiring the hydrogel itself in a curing agent, making it very useful for ease of access and reproducibility. Finally, some good examples of this being used in the fields of medicine is in wound care, where they would strap a bunch of hydrogel onto a bandage and incorporate things such as painkillers onto them to allow for pain relief over a delayed release. So overall, hydrogels are just a mixture of a porous polymer and water, where the hydrogel strand will interact with ions to create a shell or a monomer. And these monomer strands will then create multiple strands through interactive forces such as ion interactions and hydrogen bonding. So our use was through the use of physical connections rather than chemical connections.
For our porous polymer of choice in our research, we chose sodium alginate. When we talk about a sodium alginate bead, we're talking about the buildup of this alginate material. When you have just one strand of alginate, it's not much by itself, but once you incorporate those calcium ions, you'll have something called a dimer. Once you have enough dimers built upon each other, you'll have something called an egg box multimer. An egg box multimer is just a thicker layer of those alginate strands, which have kind of nestled calcium ions, kind of like an egg box with eggs. Once you have enough of these layers, they will soon get big enough to kind of come back around and link to each other to encapsulate whatever it is you choose for a model drug. In our case, we chose a green dye. To make our sodium alginate beads, you have to find a way to put sodium alginate and calcium chloride together. So as has been mentioned in many of our colleagues' presentations, we used a syringe pump to suck up an appropriate amount of sodium alginate and load it onto our machine at a set rate and diameter to ensure that our beads were all identical and hold the exact same amount of sodium alginate. And be roughly the same shape and size to prevent any confounding variables. This was the exact same method we used when we wanted to start changing our variables. So the purpose of our research specifically was to see how magnetic materials might affect the release of our beads after a magnetic field was applied. So to make these magnetic beads, we blended in, along with our base sodium alginate solution, we added iron oxide. They're very small black particles, and we just made them the same way. The issue that we started to face was ensuring each bead had the exact same amount of iron oxide particles in them. And this was actually kind of the biggest challenge in our research to getting good data.
So along with the issue of getting the right concentration of iron filaments, we also ran into many different issues with how these beads formed within our solutions. So within the middle, we had the issue of the sodium alginate droplets being brought in by its own magnetic forces to make little curvatures. So that would lead to us making different size shaped beads, which, as we know, had a different release rate. So in order to fix this, we added a needle nose syringe to distance the sodium alginate droplets from the rest of the sodium alginate syringe. This really helped us create better shaped beads and create a consistency with them. Secondly, we ran into the issue of concentration through our storage because we ran into the issue of how do we store this for a long period of time and reuse this. So first we tried a stir bar on a magnetic pad, but we quickly ran into the issue of iron filaments being pulled out by a magnetic source. So this ran into the issue of we had a lot of concentration of iron filaments on the bottom and none at the top. When we tried to do this with just same-day blended sodium alginate, we ended up with a really good result of the beads being produced and being magnetic. However, after a day or two in the stir bar, all of the iron filaments had been pulled out, so all the magnetic effects just went away. Oh, okay.
Yep, so as Matthew mentioned, we had some really great magnetic beads to start with, but after a while, the iron oxide would kind of become a sediment, and so each bead we made from a day or 2 day old magnetic sodium alginate, we would have kind of dud beads that did not show any type of magnetic characteristics. What we did find, instead of how a magnetic field might affect these, was that the amount of iron oxide applied to these beads had no effect on our overall control data. So our release, depending on if it was a dud bead that wasn't very magnetic or if it was very highly magnetic, they both had roughly the same release profile. This is really good because this opens up a huge avenue for us to create more beads that are very magnetic and slightly magnetic, and actually apply a magnetic field that time. And we'll have a set control. No matter how much we add, we'll know it won't affect how much it absorbs. Ultimately, hydrogels are really good. They're super useful in the medical field. You can do a lot with them. They are so applicable for undergraduates. You can do them in your graduate labs even. It's a really easy process that you can reproduce over and over again and get the same type of results. Which, the more that we investigate, we'll be able to find new facets about hydrogels that will maybe apply to future medicines and other applications.
And overall, while we really want to look over it on a hydrogel overall basis, us two in particular really want to go more into the magnetic bead aspect and see how it affects targeted release within things such as medicine, where people want to do cancer research. So they would want a targeted release in a certain area to prevent negative outcomes to the rest of the body. So I feel like magnetic beads overall should be more investigated, and we should see the effect of them overall. So I would like to thank you all, and we'll be happy to answer any questions.
I'd also like to thank Dr. B and the drug delivery group for all their help. So.
I did forget that. Thank you.
Any questions?
Thank you for a very nice presentation. How big is an iron oxide filament, and especially how big is it compared to your bead?
So we had got a 5-pound bag of Fe3O4. So there's just a bunch of iron oxides that were like roughly the size of like a grain of rice, really. But it was like, you know how those like little marbles we all used to play as a kid? It was just a little sliver of iron oxide within each one.
Yeah, and I'm thinking about a grain of rice, and I'm thinking about what I heard earlier, that beads are maybe 2 millimeters.
I think it was probably closer to smaller than a grain of sand even. This was a very fine particle that you could only really see once you'd clump them up together.
Okay. So could you have a lot of them in one bead? Is it that small?
Yes, so we had wanted to have 1 gram in our 2 weight percent sodium alginate solution. You could theoretically continue to add more and more until you had maybe even a black looking bead. But that was kind of the frustrating part, was trying to ensure that every bead that you made after that was getting the same, amount of iron oxide particle in it.
Can I ask a basic question? Probably, maybe I missed it at the beginning of the talk. The reason you're interested in magnetic particle loaded beads, does it have something to do with how you would direct it in the body, or why do I want a magnet?
Yes, so we had magnetic beads are very useful for simulating how magnetic treatments in the body work. So as you ingest it, it would go through the system and oh, okay. So when you ingest it, it would go throughout the system, and then at the area you want it targeted, you would place the magnetic. You would put the magnetic field there, and it would hopefully release more concentration within that area, giving more concentrated drug release in that area.
Yeah. Thank you.
Hi, thank you for a really nice presentation. I thought your data on like the absorbance was really interesting, and I was wondering, how does that tell you how much of the model drug or the dye is essentially coming out of the beads?
Yeah, so actually, kind of the reason that we use absorbance at all is because of Beer's law. We know that there's a direct correlation between absorbance and concentration. So you will create something called a calibration curve, where you model the amount of concentration of dye and then what absorbance it gives you. And using this curve, you can kind of take this absorbance data, punch it into the equation that you find, and it'll give you a concentration value out. So that is, if we took all these numbers into that equation, we could have another y-axis that was just a bunch of concentration values.
Awesome, thank you.
Questions? Thank you.
Well, thank you for hanging in there with us. And our last presentation for the evening is Ivana Dominic, and her title of her presentation is Phase Equilibria and Thermodynamic Analysis of Hydrofluorocarbon Ionic Liquid Systems.
Alrighty, hello everyone. Like Dr. Shiflett said, my name is Ivana Dominic, and this is my presentation. Little overview, I'll be discussing the research goal, methodology, go over a process and instrumentation diagram, conclusion, future work, acknowledgements, and then last but not least, the thank yous for the presentation. So our research goal for this experiment was to measure the solubilities of the hydrofluorocarbon in our ternary mixtures of our hydrofluorocarbon refrigerants and the ionic liquid in a variable volume cell, or VVC, and utilizing gas chromatography. The reason why we were doing this is to optimize our performance in the extractive distillation and ionic liquid system to help us optimize the separation of these high global warming potential refrigerants. So onto the methodology. Specifically, this is our apparatus, our variable volume cell. Here we have our gas chromatograph. You can see the variable volume cell. And then we have our oven and our densimeter that we use to measure our densities. So our hydrofluorocarbon solubilities are measured for our 3 different isotherms. We have 25, 50, and 75 degrees Celsius with measurements up to 30 bars. Specifically for this experiment, we were focusing on the refrigerants, hydrofluorocarbon 32, hydrofluorocarbon 125, which is an azeotropic mixture that comprises hydrofluorocarbon 410A. And then this is the ionic liquid that we've been focusing on. It's EMIM TF2N. So here is a piping and instrumentation diagram, or PID diagram, for our apparatus. So here you can see we have our vapor loop and our liquid loop as well. We have our helium gas and we have our gas chromatograph as well. And then we have a recirculating pump, which helps to recirculate our ionic liquid. And the reason why we recirculate ionic liquid is it helps the cell achieve equilibrium faster, which is helpful for our measurements. And having the vapor and the liquid loop allows us to sample the liquid and the vapor phases in our gas chromatograph. And so here are the calibration curves for hydrofluorocarbon 32. We use these calibration curves to help us with our results and our measurements. So as you can see, the calibration curves, we use those to find our calibration factor, which is the slope of the line. So here we have our direct relationship between the area counts and the amount injected. We use the gas chromatograph to help us determine the number of moles for each of our sample, which we're going to use to optimize our EDIL system. And so the slopes for each of the lines, we get the calibration factor, which we can use the calibration factor, multiplying that by the area counts, which is an output we get from our GC, to help us determine the amount ejected for the moles. And we were able to do these for 25, 50, and 75 degrees Celsius, the 3 isotherms that we measured in this experiment. Similarly, for the vapor loop, our gas carrier conditions were 20 psi and then 100 degrees Celsius oven. So our observations were there was no TCD saturation, and we had similar calibration factors, or our slopes, for the vapor and the liquid loop. And the liquid loop is the one on the bottom. And then our calibration curves for hydrofluorocarbon 125. Here we have our calibration curves for up to 30 bars, similar operating conditions with a sample volume of 50 microliters for our loop. And then we were able to determine that there is a similar calibration factor, or our slopes, found for the vapor and the liquid loops. So now onto the results. So based on what we have here, we have our vapor-liquid equilibrium with a mixture of hydrofluorocarbon 32, our refrigerant, and our ionic liquid. And using our pressure values, we were able to calculate the number of moles using both our data from the gas chromatograph and also the RefPro software with inputs of temperature and pressure. And so our mass balance for the vapor loop, we utilized our amount injected, or we calculated that by using our area that we got as our gas chromatograph output, and we multiplied that by the calibration factors that we showed in the earlier graph. And then for the RefPro software, we got our densities using the software, and then we calculated the amount injected using our mass of our sample, as well as the molecular weight for hydrofluorocarbon 32, the pure component that we determined the values for the moles. Similarly, using the liquid loop, for the hydrofluorocarbon 32 and the refrigerant, or the ionic liquid, we were able to determine the solubility here, which matched the literature values that we got from Dr. Alberguti in 2024 using the PETPA system. And so this is kind of the mass balance of the liquid loop that we used for our solubility calculations. So we used the moles of the refrigerant, and we divided that by the sum of the moles of the refrigerant and the moles of the ionic liquid. And then our mass of the mixture, we again used our density from our mixtures, and then we multiplied that by our liquid loop volume, which was about 53 microliters. And then our density from the mixtures, we got those from literature values. So in conclusion, our calibration curves provided us with an accurate calibration factor. We were able to deduce that from the slope of the line. We saw a clear direct relationship between our area counts and our amount injected for our moles. And then our vapor loop mass balance was consistent with that for the gas chromatograph and the RefPro software. And then our results from the liquid loop allowed us for the direct measurement of our solubility in this ionic liquid, EMIM TF2N, which directly matched the data found from literature and Dr. Albergudi's research in 2024. Our future work is to complete the experiments at the additional isotherms of 50 degrees Celsius and 75 degrees Celsius, and to continue more work on hydrofluorocarbon 125 to truly capture the effects of temperature on solubility and VLE for binary hydrofluorocarbon and ionic liquid systems. And then we'll continue to conduct these experiments across a broader range of compositions and different pressures. Lastly, for acknowledgements, I'd like to thank my mentor, Julia, Professor Shiflett, Professor Skirdo, and Dr. Barghouti. Thank you all for your time. Anyone have any questions? Guess everyone wants to go home. Okay.
Thank you.
What was the most difficult part of the experiment?
That is a great question. I personally did a lot more of the calculation side of things, and I think definitely trying to figure out kind of the calculations, think back to previous sampling that we've done, especially with the initial calibration curves that we did, which was like my sophomore year, second semester, trying to go back to that, use the calibration factor, and then go from there. I think that probably was the hardest part for me. Thank you.
Well, I would like to thank everybody for hanging in there with us. We finished 1 minute early, so fantastic job to all the speakers to get through 10 presentations on time. That's a great job in terms of practicing. I would like to thank a few people who put a lot of time and effort into putting this all together. So I don't know if Lacey is still here. Lacey, thank you for all the organization of the presentations. I thought everything went extremely well. Also, I'd like to thank Emily and Tiffany for being here and helping with everything from the food preparation to having this on YouTube tonight. And then finally, Brian, thank you for being here and filming this. Good to see you again. So with that, we conclude, and we'll do it again in the spring. So wishing everybody best of luck on your finals, and have a really nice break. And then we look forward to seeing you back, I guess, on January 20th when school starts, and then we'll do this again in the spring. So good night, everybody.